finally, the assumptions about this noise thing, this residual, which actually, makes our econometric necessary. Well, without u, we could just calculate how large beta is. It would be a deterministic relation, but of course, in practice, no, it's stochastic. And here we have very important assumptions to a variant about, we talk about the exogeneity of the regressor. And first, we consider the case that the regressors are actually strictly exogenous. And see what that means in math terms. It means that the expected value of u is 0, conditioned on x, for all x. So this assumption here, the strict exogeneity, here implies not only that the expected value of the u is 0, but also that the covariance between the error and the regressor is 0 for all x, right? And this is here a little bit loosely in the notation. It's indicated that here's I and j. So this means that not only, as you know from Econometric 101, that the regressor is uncorrelated with the residual, so that ui is uncorrelated with xi. But this here implies that the residual is uncorrelated with all regressors, but also with past and future and all these, right? So this assumption is that's very strong assumption, very strict assumption that moves out that our model includes lag endogenous variables. So for time series analysis, we will see this is just the assumption makes no sense. Nevertheless, in Econometric Bachelor, we talk a lot about exogenous regressors in the sense that they are not random, right? This is one of the standard assumptions as I teach it, because 95% of all the results that are relevant in the bachelor course can be derived and illustrated under the assumption that the regressors are non-stochastic or not random. And if you have x not random, then all the conditioning here makes no sense, it's not necessary, right? Because if you have a random u and a not random x, by construction, by assumption, there is no correlation. Only random variables can be correlated, right? Not something which is uncorrelated. Yeah, not random, I mean, yeah.
For this case, can I equals the g? You mean it's for all cases?
Yeah, it's for all cases. So this here is a special case of that one. Okay, so j goes from 1 to n. Right? So you take it. Also I. Everything. All. This is what makes it so strict. Right? So this is strict exogeneity. This is what we need. An alternative assumption about the regressor is meager form, and this is what we will actually need in most applications. Weak exogeneity means that only the regressor, the residual with the corresponding regressor. So in the same equation, the same time period, for example, are uncorrelated. Right? Okay, here are further assumptions about the errors, which should be known from, or looks familiar from the bachelor course. There is no serial correlation in the errors here, which implies that omega, the covariance matrix of the U's, is a diagonal matrix. Yeah? Because the off-diagonal elements of the covariance matrix, they are the covariances between two different random variables, right? On the diagonal of the covariance matrix, so these are the E's diagonal, so the I's diagonal element of covariance matrix of the U's. There are the variances, and here you see the standard assumption of homoscedasticity. So there is no heteroscedasticity, meaning that the variance of the U is always the same for the first, for the second, for the third, and so on and so on. Right? So finally, an assumption assumption, which is not so important for most for results, but useful for some, is that the distribution, so far we only talked about, so far we only talked about the first two moments, so about the expected value and about the variance of the u, but not about the distribution. We don't talk about chi-square, t, normal, whatever, For many results it's very useful to assume that the distribution of t is known and that it's normal. Okay? Just as a reminder, please think about the economic intuition about these assumptions. Yeah? So here, for example, homoscedasticity of the errors. How would you explain to someone which is not an economist, not an econometrician, what is the essence of this homoscedastic assumption here about the errors? How would you explain? Remember, you will be master of economics in 2 or 3 years, right? And then your job will be usually talk with non-economists. Okay, so if you do something, you have to explain it in a way that people understand. So how to explain homoscedasticity? Look, this is the variance of the u. The variance tells me something about the uncertainty, about the volatility, about the fluctuation, about the uncertainty, right? If the variance would be 0, there would be no, and the expectation of the u is 0. Well, if the variance is 0, then the u's would be always 0, right? Okay. Variance 0 makes no sense. So variance a little bit larger than 0, right? Positive, larger. So there is some variation in the u. Okay. So now assume that here, that homoscedasticity assumption says that whatever observation I look at, the first, the second, the third, the fourth, for each I, the uncertainty in the residual, in the deviation from my model, is always the same. Okay? Implying that the information content of each observation is in principle equal. It's the same. Look, if you would have heteroscedasticity, right? So the classic assumption in the bachelor is you have a regression, food expenditure on income. I guess this is the example in the bachelor course, right? Food expenditure on income. Well, if you would plot such a data set, right? So you have 30 people and you ask them what's the food expenditure, what's the income. Well, you will see a positive relation. The higher the income, right, on average, the higher the expenditure on food. All right? But if you would look at this figure, you will see that the information content about that relation for poorer guys is higher than for richer guys. Why? Because a rich guy can, at some months, spend a lot of money for food, champagne party, right? Whoop, very high. And in some months where there's no party, rich guy party, he might spend more or less the same money as a poor guy. He also goes to ID for some reason, right? So no party, ID, very small party. So the volatility, the variation, the information content in the consumption behavior of a rich guy is much more uncertain, the information is much lower than for poor people who more or less always spend the same fraction for food because there is no variation, there is no champagne party. They always go to the food. Okay? That's the economics, right? And this is what we assume here when we assume homoscedasticity. Each observation is of equal quality, so to say, of same information content. Right? It's not that we have one observation where we say, well, I don't know whether I should trust, right? High sequence square. And some which are very reliable and informative. No sequence. No, here, everyone's equal. Okay, so causality is here by assumption no problem. Clarified. Okay, we have here exogeneity. Morning. Exogeneity x relative to x. Okay. So under these assumptions, we are able to derive properties of our least square estimator, right? And the first property we talked about was unbiasedness. And we also discussed, how to explain non-economics, right? What unbiased means, right? Remember, right? On average, if we would repeat our experiment a lot of times, then on average it would be close to the true value. It's not the most, that value is the highest probability or whatever, something like that. No. Okay, so this is what we want to have. If we just assume that there are 100 researchers who do exactly the same thing with different data, which is, randomly picked from the population, and on average, our estimate would be okay. There is no systematic under or overestimation like here. All right, so that was, I guess, the last slide from last week. So first, we want to check under which assumptions is the least square estimator an unbiased estimator of the true beta. Okay, so here's our model, and here's our assumption. So you see, I write exogenous, but I mean strictly exogenous, right? So I should write better here, strictly exogenous to make clear. It's really strict exogeneity here. So the U's are uncorrelated with all the regressors. All right? So this is the least square estimator we derived in the last chapter, in the last section. So if you just plug in what y is, you see that you can rewrite the least square estimator like this. Okay? So that holds always, irrespective of any assumptions about exogeneity. It's just maths, right? But now we want to know what is the expected value of beta hat. So what comes out on average? Is there a systematic bias or not? And well, you see, expected value of beta hat is beta if and only if the expected value of this animal here is 0. If this is non-zero, then obviously there's a bias. If it's 0, then it's unbiased. And here you see the proof of the unbiasedness. So, expected value of beta hat conditional on x, this is conditional on x also. So, minus beta, this is a bias, right? Okay, well let's see whether that bias is 0. So, if you subtract from beta hat beta, you see that really just this here remains, right? So you want to know whether the expected value of this here, given x, is 0. Okay, so nothing happened here, we just plugged in this here. Now we use that we condition on x. So condition on x means that we can pull out here, factor out these x prime, x minus 1, x over, before the expected value operator. So this is exactly this here. And now you see, in Bachelor 101, we say, expected value of u is 0, proof finish. Right? Here it's a little bit more tricky, because x is some variable, maybe random, right? Here you see that that we have unbiasedness of the least square estimator. In fact, if and only if the regressor is strictly exogenous. Right? So this here is 0, if and only if this is 0. So this is the definition of strictly exogenous. Okay? So, first result. The square estimator is unbiased if and only if regressors are strictly exogenous. Okay, so this is first, well, this strict exogeneity, sounds a little bit, very restrictive somehow, right? But there are also good news here. For example, remember the bachelor thing, if we knew for whatever reason that the x's are in fact not random, like dummies or linear trend or something like that, you know, or we just know, then, of course, X is always exogenous. Well, and this is in fact the reason why in many bachelor textbooks, right, there is the assumption that X is not random. And randomness of X is only introduced in chapter 8, 9, 10, 11, or whatever, right, after having established everything. All right, second good news is that if you look at the proof, and this is the beauty of proofs, that we can really check why is that proposition true. So you see that in the proof, we didn't use the assumption of no order correlation and no heteroscedasticity. Right? There is no covariance, there is no variance here. We don't need it. So in fact, right, it is obvious from the proof that this here holds even if the U's are heteroscedastic and even if they are autocorrelated. These are assumptions we do not need for unbiasedness. Okay? Good news. Right? It doesn't matter whether, oh, I have heteroscedastic errors, still unbiased. Okay? If the regressors are strictly exogenous. Alright? But as we already discussed, you know, these were the good news. The bad news is that strict exogeneity is a very hard assumption for regressors, which in particular rules out any time series data where you have lagged endogenous regressors. Okay, so, well, we said unbiased if and only if strict exogeneity, strict exogenous regressors. So that implies that if we don't have strict exogenous regressors, if we estimate a time series model with lag endogenous variable, then we have a biased estimator. And this is exactly illustrated here in this simulation study. Look what it's done. Again, notation is a little weird here, I have to admit. So we have a linear regression model, right? Okay, now alpha is the parameter that we want to estimate, and x are the regressors, but we have only one regressor here for our simulation study. And that regressor is just the value of y the period is before. So think of E as a time series, because we have really the ordering from I 1, 2, 3, 4, 5, 6. It doesn't, yeah. So therefore, think of a time series that makes the most easy. So look, if the regressor is a lag endogenous variable, then we discussed last week that this implies that there is no strict or strong exogeneity. I should write strict, right? Strict, strong, mean the same, right? So the assumption of strong exogeneity, strict exogeneity is violated because of these endogenous regressors, right? So I guess we also discussed in detail on the whiteboard last week why when we estimate the autoregressive model like that, yt is alpha yt minus 1 plus ut. So that is a model in the more traditional, more established notation. This model we estimate is yt minus 1 plus ut. Well, yeah, and yt minus 1, yeah, it might be uncorrelated with ut, right? But it is correlated with ut minus 1. Yeah, because, well, ut, if this holds, then of course also that holds. Ut minus 2 plus ut minus 1. And here you see, well, obviously they're correlated, right? And remember, strict exogeneity means, well, yt minus 1 is uncorrelated with all the u's, not only that one. Oh, and this is obviously yt. Okay? So, how does the simulation study works? We do everything we do 5,000 times. Right? So what do? We have a simulation study that starts with n observations, and we increase the number of observations successively. Right? So very small data, so there's some random generator that gives us the epsilons. No, I think you did that already with Lea, huh? Did you already simulation study with Lea in the tutorial? With R? Hello, everybody here. Yes, no?
Last week we had a problem, I think. Last week we had a problem with R.
With R, ah, okay.
Yeah, therefore we couldn't do
Okay, but this is something you should do. This is one of the major reasons why we use R. Yeah, because it's so easy to do something like this. Yeah, it's not so easy to do it with more applied software programs like SCADA or EDUs or something like that. Right? Okay, so that's easily done with R. Okay, so and then for each of these realizations of our simulated time series, we estimate the alpha. So we, as always in simulation studies, we know the truth, but then we take a step back and we, we just do so as if we don't know. We just estimate them. Yeah, and the estimated, the ordinary square estimator of that alpha is called alpha hat. And of course, for each simulation, M, we have a different time series, we have a different estimate. And also, it also depends on N, because we re-estimated each time for N, for 10 observations, then we use 15 observations, then we use 20 observations, and so on. Alright? Okay. So, what is the mean of the alpha? The mean of the alpha here is, so for each of the estimates, for a given number of observations, so assume we have 10 observations, then we have 5,000 estimations for 10 observations. This is the average, right? So we have 5,000 estimates of the alphas for a given n, and we divide by 5,000, and this is obviously the average. So what we do here is exactly the Gedanken experiment when we explain what does unbiasedness mean, right? We do we generate these random variables, these random observations, and re-estimate these things 5,000 times. Taking the average, if it's unbiased, it should be very close to the true value, which is 0.9. So, this is the mean, so to say, the expected value, of our estimator. So the bias is, of course, then expected value minus true value. Okay? Yeah? Here's the result. So, here you see the numbers, the estimation for varying sample size. Right? So remember, we started with 10, we had 10, 20, 30, up to 100. Okay, that was the maximum number of observations we used for the estimation. Here you see what comes out in that using the same data when we put alpha to 0. Right? So when alpha is 0, then yt minus 1 has no impact here. Then the yt is just random noise, right? And the true value is 0. And you see, well, in that case, if this is here gone, then we have no endogeneity problems, right? Then these square estimators should be unbiased. And look here. Here is a bias. So this is the mean of our simulation, the expected value, minus the true parameter, which is 0.9. And if there is no problem with the regressor as well, there is no problem with the least square estimator. The bias is 0. Okay? So if the true value is 0, we estimate 0. But what if the true value is 0.9? So that's the interesting case, right? You see, the bias is, well, significant, I would say. Right? So here, the bias, what is that? Minus 0.1 something, right? So on average, taking the average about these 5,000 simulations of the same process with different random numbers, we see that there's a clear tendency to overestimate, no, to underestimate, sorry, over, under, this is negative, so we underestimate the p-value. Yeah? It's minus 0.1, so here if you take the difference between these two, it's negative, so this is larger than that. Okay, bias. We have a negative bias in our estimation, and the reason is the alpha. The lag induction is variable. But now look how this bias behaves if the number of observations increases. Right? See, if the number of observations increases, then the bias gets smaller and smaller and smaller and smaller. If you look at that figure, you might be interested in what happens if n goes even larger, right? So is it converging to something like minus point something or what? So looking at these fine samples, it's not clear so far whether that bias actually diminishes, fades out, if the number of observations goes to infinity or something like that. This is something we check. Okay. This experiment is rather famous, and you could show, or Griffith showed, that this bias asymptotically, so if t is large but not infinite, right, that this is approximately here minus 1 over blah, 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 blah. T is now the number of observations, right, because this is a typical time series experiment here. Yeah, you see that, look here, if alpha is 0, no bias. The larger alpha, the larger the bias. Okay, because the larger, the higher is the covariance between yt minus 1 and tt minus 1. Okay, so classical example here for the so-called small sample bias of the least square estimator in case of lag endogenous variables. All right, so we talk about weak exogeneity, you know, and why we, in which cases weak exogeneity helps us to derive nice properties of these estimators soon. Before we do that, we stick to the fine example thing and talk about the variance of least square. The variance of least square estimator is, of course, when we have a vector, when we have several regressors, then beta hat, then beta hat is a vector. Yeah, for each regressor we have one number, we have one beta 1, beta k, and then the variance is of course actually a covariance matrix, right? So if we have k regressors, what is the dimension of the covariance matrix beta of beta hat? If we have k regressors, what's the dimension? No? You know? You don't know? Remember, I need your feedback, right? First of all, to keep you awake. And second, to get some idea whether this is just, you know, oh, come on, let's go, it's all bachelor stuff here or what, right? Or whether it's difficult. So, what do you think? What's the dimension of the covariance matrix? It's k times k. Right? Because we have k regressor, so we have k beta 1, 2, for each beta 1k, and then you have k variances for each beta 1 variance, and of course we have all these covariants between beta 1, beta 2, so in effect you have a k times k matrix. Okay? So please check when you go through your slides, because you work on slides, right? Then always check, you know, all these symbols. Do I understand? Do I know what that is? Right? Is it a number or quadratic matrix or non-quadratic or dimension? You know, if you can't answer this, then actually you don't know what you're talking about. Okay? covariance matrix, therefore, all these betas. And you see, we still are under the standard assumptions, so we assume for simplicity we have unbiased estimator, exogenous regressors, strictly exogenous regressors, and we are in this nice case where the variances are all the same and there's no order variation. Okay, so the covariance matrix of the U's is diagonal. And just as a small reminder, look here, this is the identity matrix, right? This is n, the number of observations, and you see we have n U's for each observation, one U. So the covariance matrix of these U's is of course n times n. Right? If I have 1,000 observations, this is the 1,000 times 1,000 matrix. If I have 2 regressors, this is the 2 times 2 matrix. Yeah? All right. Okay, so now let us derive, just, yeah, this sounds, it's called proof, but actually it's just plugging in and calculating it, right? What is the covariance of beta hat given x? Always given x, because it has to be a conditional variance, like a conditional expectation, because x is a random variable, right? So the answer will depend on x. Okay, so here is the definition of the covariance matrix. It is the outer product of the expected value of these derivations. This is really, if you plug in numbers, this is just, that is just the definition, the statistic 101 definition, so to say, for variance. So nothing happened here. The only thing that happened here, which is worth emphasizing, is that we subtract beta. Because in general, you have expected value of beta hat minus expected value of beta hat times and so on. Okay, that is actually the very, very general definition of a covariance matrix. So you have your random estimator and you subtract its expected value. Yeah, because you want to talk about variance, so it's always about deviations from the expected value. Right? Then you see we have here now expected value of beta hat, we plugged in beta. Yeah, and this is a consequence of our proposition before. Because we just showed if we have exogenous regressors in our linear regression model, then the b-square estimator is unbiased. Okay, and unbiased means the expected value of beta hat is just beta. And this is why it's minus beta. Right? Okay? So, this is just, as I said, this is just the definition, and please check, again, this is matrix algebra a little bit. If you have, this is a vector, beta hat minus beta is a vector, k-dimensional vector. This is also a k-dimensional vector, but transposed. So you have something like this, multiplied by that. Usually we do this when we multiply, right? So this would be the inner product. Vector, beta prime, so if the prime would be in the first parenthesis, then it would be like this. Then the result of the inner product of these two vectors would be just a number. Right? Scalar product of two vectors. X prime x. But x prime is a so-called outer product. So now you are in this situation. And then the result is a k times k matrix. And this k times k matrix is exactly the covariance matrix. Yeah? Alright. So now we plug in what we know about beta hat minus beta. These are the same expressions that we just used in the proof of unbiasedness. just the difference between beta hat and beta. Go one slide back. Here, look, this is that one here. Beta hat minus beta is just this, and this is what we just plugged in here. Okay? Again, nothing special happened. We used here the unbiasedness of the estimator, and that's it. Right? So, and now we multiply out. Okay? So, the only thing we now use is the expected value, well, again, expected value of this animal here, conditioned on x. You can factorize out these x prime x, all the things which depend on x, right? So I can try to do it on the whiteboard. So we have, okay, variance, or better covariance matrix, beta hat is an x, is the expected value of x prime x minus 1, x prime u x, x prime x minus 1, x u. Yeah? This is on the slide. Now, this is here conditioned on x, so I can write this as x prime x 1 x prime times the expected value of u prime times x prime x minus 1. That's right? Yeah. So, and now you see, now I really need the assumption about the errors. For unbiasedness, it didn't matter whether it was homoscedastic or not, correlated or not, but now, in order to come from this line to that line, I have to use this assumption, namely that the covariance matrix of the u's, which is again the outer product, the expected value of the outer product, right? It's not u prime u would be the sum of the squared residuals, would be a number, right? But u prime is the outer product. This is the n times n matrix, right? And because of homoscedasticity and no order correlation, we know that this is a diagonal matrix. So this is just x prime x minus 1 x prime sigma square x prime x minus 1. And now you see this is sigma, this is just a number. This is the identity matrix, right? You can forget that, right? So this is sigma squared times x prime x minus 1 x prime x prime x minus 1. And here we are. X prime x inverse times x prime x cancels out. It's the identity matrix, and therefore what's remaining is just here. The variance, the covariance matrix beta hat is just sigma squared times x prime x minus 1. Again, this result should be known from the bachelor. However, though I prove it in the bachelor without conditioning on something, because I would just assume it's a not random variable and therefore everything is a little bit easier in the notation, right? But the result is the same. Okay, so that's the covariance matrix of beta hat. Sigma squared times x prime x minus 1. Okay? So look, this is a k times k matrix, of course, right? If you're not sure, check. If you look, if you now look at that formula, and it's our task as economists not only to devise the formula and say that's it, but
we said it's the strict exogenous, but then we got beta hat equals beta. Why not?
It's
equals
not beta hat
zero?
equals beta, it's expected value of beta hat is beta. Because of the strict exogeneity, this was that one here, because we assumed strict exogeneity, we know that the expected value of beta hat is beta. And this explains why here it's not the expected value of beta hat, it's just beta. So, but I don't know whether that was the question, but I just want to correct the mistake you made in your question. So
My question is,
Yeah.
I thought beta hot minus beta should be zero.
no, it's the expected value of beta hat.
Yes, I know.
Beta hat is just, beta hat for a given data set is just a number which fluctuates. Depending on your randomly chosen observations, like it's really therefore these simulation studies are so useful, because in a way they mimic the situation you can't do in practice. Yeah, in practice you have 1,000 observations of people, blah blah blah, and that's it. Right? You have no chance to say, right, this is 1,000 observations, and now I take another 1,000 observations. No, there's only one survey, and you can redo it 5,000 times as we did in the simulation thing, right? So this is the expected value of beta hat, which should be here, and because we assumed exogenous regressors, that's the same. Okay? Good. So, now let's talk about our result. So first of all, it states here, the more variation in the error U, the larger the covariance of beta hat. So, the more variation in the error U, well, that shows up, of course, in the sigma square, right? If you have something like this, you should think about, does it make sense? Do I understand, right? Suppose, and that's an exercise which is in many cases useful, if you have something like this, it's a variance. Sigma squared is a variance. So it's a positive number. What happens if that positive number goes to 0? What happens if that positive number goes to infinity? What happens with that? Do I understand? Is there some intuition? Right? If not, problem. Yeah, because then you just don't understand what's going on. Okay? So what's going on if sigma squared goes to 0? It's very, 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 very small. What happens with the variances of the estimator? Yeah?
They go also approximately to 0.
And does it make sense?
Yeah, for sure. If our errors, which are included in our calculation or estimation of our estimator, beta hat, are going close to 0, then beta hat I, for example, equals more and more beta hat y. if that makes some sense. So regarding our sample, which we take to estimate beta hat, there's less and less variance between these samples.
Okay.
So therefore,
I think you're on the right track, but think about, your task would have been, explain the intuition of that formula to a non-math guy. Right? It would be difficult, right?
Right.
So, another suggestion would be, sigma square is a variance of disease, right? The higher sigma square, the more variation in the U. The more variation in the U's, the more difficult it is for us to see what is the correct beta, what is the true beta, right? If sigma square goes to 0, that means there are only tiny variations. These U's are super small around 0. Come on, it's, if you would in the bivariate thing, if you plot your data, it would be just on the line, right? Because there's those tiny variations. So it's obviously not a problem to just spot the beta, the true beta. There is no uncertainty left. We just see the beta, right? Oh, and vice versa, if sigma squared goes to infinity, it gets more and more difficult, right, to estimate the true parameter beta. The variations in our, if you would simulate that with larger variance, well, that would be the bivariate thing. That would mean that the scalar plot get more and more diverse. So it gets more and more difficult to spot what is the true regression line, what is the true slope of the regression line, implying that our uncertainty about the estimation gets larger and larger and larger and larger. You want to ask a question?
I was just wondering, like, how would the matrix look like if sigma goes to 0?
That one here?
Yeah.
If sigma goes to 0, you see that they are unrelated, right? So x are just, this is just our data. X.
I mean, this overall term describes the covariance matrix.
Right?
So I was wondering, if I look at the covariance matrix, could I see if the sigma goes to 0 or to infinity?
No. If you just look at that, here is the k times k matrix, and this is the covariance matrix. You know that each of the entries is a product of coming from x prime x multiplied with sigma squared.
Yeah.
So, a task which is still open is how to estimate sigma squared. We can't do this, right? But so far, you're true. That's right. We only have an estimate for the whole thing. But as we know how the formula looks like, we can still do this comparative static experiments in our head. What if, right? Okay. So good news, right? We somehow understand that comparative static with respect to sigma squared makes sense. Okay? This is not obviously stupid. What's here? Okay? Good news. Not always so obvious in economics, because it's not stupid. Alright. Actually, you can say more. If sigma squared gets larger, so what you immediately see is that, yeah, well, then it gets larger, the variance, right? But actually, you can say more. For this, you can do this trick here. So you see, if we expand that formula here by n, you see we multiply both terms with 1 over n, and because this is inverted, we have here n times 1 over n, and it just cancels out. Okay? So this here is exactly the same as this here, because of this 1 over n minus 1. Now, recall what we assumed about the behavior of x prime x if n goes to infinity. Right? That should be a well-behaved thing. And this shows you somehow that if you double the sample size, right? So if you go from n to 2n, then you halven the variances. Yeah. If you assume that this is stable, if n goes to infinity, this is stable because it's well-behaved. So that converges to something, then you see that times. This is a result, that's just, a footnote, right? Because it's really a strong assumption, and you say n goes to infinity, it's actually an asymptotic approximation. So it's just, this is all you can say. It's not so much. But the main point is that you understand the comparative statics, or when it goes to 0 and it goes to infinity. Okay, cool. So what else can we say? So far we talked about sigma squared. Let's now talk about x prime x. Okay? So look, we have to invert something, right? So that matrix we have to invert is therefore, well, if everything is nice, invertible. So what does it mean if this here gets, well, large? X prime x gets large. That means that x prime x gets small. Right? So if regressors are highly correlated, that would exactly imply that x prime x is close close to being a singular matrix. Right? I think we discussed it already when we talked about x prime x in the last chapter. Right? If you have two regressors, x2, x3, which are very similar, more or less the same, that would result, well, because they're not exactly identical, that you could still derive the square estimator, but if they are highly correlated, that would imply a lot of uncertainty in our estimation. The intuition would be the square estimator is not sure whether the impact comes from regressor 2 or regressor 3 because they're so similar, right? That would be the intuition behind that result, that high correlated regressors lead to high variance of our estimation. This is a formula you might know from the bachelor course. So this is the formula here. This is the variance. So we look here at a model with two regressors. So a constant, regressor 1, regressor 2. Okay? So the third variable is the second regressor. Okay? Because we have this constant. So if you just plug in this very special case, only two regressors and a constant, in that general formula, and if you check what the variance of beta 2 hat is, right? So remember, if you have K2, so we have three regressors, then the covariance matrix here is a 3 by 3 matrix. Yeah? The first element is a variance of the constant of the estimator for the constant. The secondary element here is a variance of beta 2 hat, and the third element would be the variance of beta 3 hat. Okay? So, if you plug in this very special case, you can derive, it's tedious but not interesting, the variance of beta hat is sigma square, okay, here, and look here. Here, somehow the variance of the x makes sense, comes in, and this term. And this R23, this is just the correlation coefficient between x2 and x3. Right? So, and now, let us, what we did here, a little bit more abstract, matrices. Just look at that number now, at that second diagonal element, in that special case where we have only two regressors. Now you see, first of all, okay, sigma squared, yeah, it's the same, it's just proportional to sigma squared. Nothing new, right? But now you see here, what is the importance here of the correlation between variable x2 and x3. If the correlation between then goes to -1 or +1, so if they are highly correlated, negative or positive doesn't matter here, obviously, right? Then this here goes to 1 in absolute value. Therefore, the square of it goes to 1. 1 minus something that is close to 1 is close to 0. Close to 0 here in the denominator blows up everything. So the higher the correlation between the two regressors, the higher the variance of beta 2 hat. And very much the same for beta 3 hat, as you might expect. Right? So the higher the correlation, the more uncertainty, because the least square estimator had a hard time to distinguish between the impact of regressor 2 and regressor 3. Okay? The third thing that matters here is, as you can see, the variance of x2. Right? So you see, the higher the variance, this formula suggests, the higher the variance in x, the better. Because large numbers here, small numbers of the variance. And we want to have small variances, right? We want to be sure about our estimate. Does that make sense to you? Usually, high variance, higher 70. But now, oh, high variance of the x. Now this is the mean of the x2. Here is the x2. So if this number is high, that means this is square deviations, right? So we have a lot of variation in the x. Does it make sense to you? Why?
I would guess if we were to have like, if our data would be like only one of the one small point, it would be difficult to
Yeah.
create.
I'm not sure whether I have a slide. So I have to do this here. So think of a regression line. Now we are back in the simple linear regression model, right? And here's x, and here's y, and we have something like that. So these are our observations. This would be a sample with a small variance in the x. X, well, this is now x2 or whatever, x. So this would be x prime then. And you see, very hard to estimate, right? Could be this, could be that, I don't know. And the reason is low variation. Ah, now much better, right? Now we know, it must be something like this. It's not this or that, right? And why can we say that? Because we have now more variation in the x. Okay. Variation in regressors, always good. Because this means that we have really variation in our data. And remember, what we want to estimate are marginal effects, slope coefficients. Beta tells me how much does y respond if x changes. And of course, the more changes I have in x in my data, the better. The more easier it is for me to estimate the data. Okay? So, high variance in the errors, problem. Sigma squared goes up. High variance in the regressors, good. Because we have a lot of variation, a lot of information in our data. Okay? If we have a regressor that is always, more or less identical, then it's very difficult for us to make a prediction about the flow of the regression. Cool. So you see, the correlation between the regressors plays a big role in determining the estimation uncertainty and the properties of the estimate. All right. So now we arrive here for finite samples, the bias in small samples, under strict exogeneity, there is no bias, and under strict exogeneity in finite samples, we have this formula for the variance. Okay? So let's go, before we talk about the large sample properties of the estimator, let us recall here some statistics which we will use in order to characterize this. We already used the variance and bias, and in many cases, in practice, there is somehow a trade-off between variance and bias. Right? So both are not good, right? We want to have an estimator which has a small variance, then we are pretty sure what it is, and also a small bias. Right? Because if the bias is huge, then it's not helpful when the variance is small. Right? So then we are with certainty wrong. Great. Okay? So, nice figure here to illustrate what low variance and what is the relation between bias and variance. Right? So look here. So you want to estimate that one, right? And your estimate is throwing the dart to that to this target. And here you see this is what we really want. We are very close on average to the true value and with a low variance. So there is no systematic thing here. It's not that we always are left, always under or upper or something like that. On average, it's alright, and all the dots are very close to the true value. Low variance, low bias. Here, we are also very certain, although low variance, right? But unfortunately, we didn't meet the target. So low variance and high bias. high variance, but unbiased. Great. So it's not, we do not systematically overshoot. And here, this is the worst thing, right? So high variance, this would come out if I show. Right? Okay. So mathematically, this leads to the mean squared error, MSE, of an estimator. And you see that the mean square error, this is a definition, a very suggestive name, because it's a mean of a square error. The mean square error, right? Look, the mean is the expected value of the squared deviation from our estimator from the true value. Okay, this is just what the formula says. Expected value of the squared deviation of the estimator from the true value. And now, if you just multiply this out, right, taking binomial formula and so on, well, it's a small exercise, right, small enough to ask in the exam, maybe, right, and then you see that this is just the variance plus bias squared. Now this is the variance, that's the definition, the very general definition of the variance of a random variable. You see, it is the expected value of the squared deviation from the random variable of its expected value. Now we don't know whether it's an unbiased or biased estimator, right? If we would know that it's an unbiased estimator, then that would be just theta, the true value. But we don't know whether it's unbiased, maybe it's a biased estimator, therefore we have to be cautious, and it's just the expected value, whatever it is. Right? That's the definition of the variance, and here is the definition of bias. So expected value of theta hat minus theta. Squared. Right? Squared because we don't care here about negative deviations or positive deviations, we just want to know how large is the bias. In absolute value or squared makes it easier. Okay, so here it again. So in the following, when we talk about consistency, so what happens with the bias, what happens with our estimator if n, the number of observation, goes to infinity, we very often use criteria that are based on the mean squared error. So in particular, so if we say something converges in mean square, this means that this here goes to 0 when the number of observation goes to infinity, right? So obviously it only looks at two moments, expected value and variance. So there's no skewness here or kurtosis or something, right? We're only interested in expected value and variance, the first two moments. And as we will see, the consistency we introduce here in econometrics, and the one that is widely used in econometrics, this concept of consistency is often verified by the fact that the mean squared error goes to 0 if n goes to infinity. And that means obviously that the variance, that both the variance and the bias goes to 0 if n goes to infinity. Okay, so there are several concepts of consistency in the mathematical literature. In econometrics, here in that course, we are happy with convergence in mean square. So if n goes to infinity, this term here goes to 0, and then we say, that's sufficient for consistency. Okay. Here is, again, I hope I remind you, at the formula you know already from the bachelor, what consistency means. So, consistency is now something, you see all the arrows and the ends. So far we only talked about finite sample properties. So given n is 1000, n is 10, whatever, we can derive all the least square estimator, we can derive the bias of the least square estimator, we can derive the small sample bias, therefore, right, because we have a finite number, and we derive the covariance matrix. Now we ask what happens if n goes to infinity. Because we saw already, in the simulation study, that bias of the least square estimator is something which is a small sample property, which might, in some cases, just vanish if n goes to infinity. Right? So let's look at the properties of our formulas and about the estimator if n goes to infinity. So therefore, from now on, for the next slides, we talk about these asymptotic properties. Sometimes people say also approximately when they mean not only just but only if n goes to infinity. Here's the definition. An estimator is consistent in the conversion probability to the true value. Conversion to probability, what does that mean? That means that the probability, look here, the probability that my estimator is larger away from the true value than some epsilon. Epsilon is a positive number, of course. However small you choose epsilon, this probability goes to 0 if the number of observations gets sufficiently large. You know, when I guess, you know, when I saw this the first time, I thought, well, what is this for a strange thing? You know, this is a very harsh thing to assume. Come on. For every epsilon, so if epsilon is 0.00000, and then the probability should be go to 0 that my estimated is more than 0 away from the true value. That's this, you know, with certainty more or less, I get the correct value. That seems to me, you know, given my experience with data, I know the fluctuations and the variances, that seems to me like a very strong thing, you know. Is there anything, does these estimators even exist, right? The truth is, well, actually, we see this here as a minimum requirement for an estimator. Whenever we see that, oh, oops, in our situation, the estimator is not consistent, then go home. Do something else, right? Never present results based on an inconsistent estimator. That's the worst thing you can do, right? So, why that? Yeah. Why that, even though it looks so extreme, right? Why is that not so extreme in fact? As we can see later, you know, under mild assumptions, we can show that our least square estimator is in fact consistent. The point here is n goes to infinity. That means, right? Remember what are the assumptions of our linear regression model. We assume we know the true model, right? The only problem is there is this noise with this u, and therefore we have to scatter plot and we have to estimate beta and so on, right? What this consistency means is that if you would have sufficiently many observations, this uncertainty goes to 0. Look, if you really consider the true relation between y and x, and all these u's are really, you know, errors which fluctuating around 0, you know, blah, 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 then the only excuse that a researcher has, and it doesn't exactly tells you what beta is I have not enough observations. That's the only excuse. Yeah. So just think about it, you know, that you know, come on, here I have 1,000 observations, and here's my estimate. Unfortunately, there are some variance in the estimation, there are some confidence bands, you know, I'm not perfectly sure. What can I do? Well, you know, I have not enough observations, and then someone comes around and says, you know what? How many observations you want to have? I give you, you know. Survey costs are high, doesn't matter. I'm Elon Musk. I pay you 1 billion of observations or whatever, you know. It doesn't matter. Then no choose anymore. Right? In practice, not possible, yeah, because we have only 100 observations for German GDP. So what can we do, right? So we are limited in practice very often, right? But in practice, so if we could increase the number of observations to infinity, then all estimation uncertainty should be gone. Okay? So here's just alternative notations. So in proofs, now this is a little bit clumsy, right? So we just abbreviate this as lim, probability limit. So we say that if this holds here, the estimator converges in probability to the true value. The plim of the estimator is the true value. Some people look, yeah. So depending on the textbook, you know, you see various ways, but it's always means the same. Okay, yeah, as I said, consistency is an asymptotic behavior. So n goes to infinity. Right? We are not talking about the case, what happens if n is 1,000, 2,000, 3,000, 1 million even, right? It's really, it goes to infinity. All right, so, but of course, you know, the empirical relevance of this concept is that we say, well, I have 1,000 observations, this is rather close to infinity, right? So, this is why people somewhere call some results approximately, because they have an asymptotic result, which they know which holds if n goes to infinity, but in practice they have, of course, not infinitely many observations, they have many observations, and they hope that many is rather close to infinity, sufficiently close to infinity. And there are, unfortunately, no rules of thumb there, what large means, right? Whenever it makes sense to argue this with asymptotic properties of the estimator. Yeah? If you have only 10 observations and you say, I know it's a bias estimator, but it's consistent, and therefore let's go. People would say, come on, consistency, n goes to infinity, you have 10 observations. What about the small sample properties of the estimator? Right? Obviously you can do that, right? And then, you know, it's a matter of taste, right? And how convincing you are in the presentation of your results, right? Whether people buy it, that you say, yeah, there might be a small set of bias, but I have so many observations, let's go for this. Approximately, that's not a problem at all. Okay, so here you see a nice, again, a simulation exercise. A simulation exercise in order to visualize somehow the concepts of unbiasedness and consistency. So that's a little bit confusing here, but what's happening is the following. 10 realization means we have 10 simulation exercises, and each of the exercises here is one color. Okay? And the exercise is, we have, here for example, we have 200, this is 200. We throw, what do? Heads over tails, so there's a coin that we toss. Right? And we just, on these 200 coins, we look how often does coin happen in heads. And of course, you know, if it's a fair coin, then it should happen 50%, right? So what you see here, however, is the excess, is a number, is a percentage of excess heads over tails. Right? So if you do it 10 times, for example, very small number here, right? Then of course you cannot expect that you have, if you do 10 times, that exactly 5 heads and 5 tails would show up, right? Of course there's a variable, it's random, right? Sometimes people get, you know, 10 heads in a row. Well, the probability for this is low, but it may happen, right? And then you have, a high number of excess. And what you see here is that the unbiasedness, right? And for each number, you know, you see the excess proportions. And the unbiasedness now means that in this these random deviations from the true value of 0, because it's a fair coin, then there should be no excess heads over tails, right? That there is no bias in the sense that this is a fairly symmetric pattern. So you have approximately as many trials where you have excess heads and not enough heads, right? Well, that makes a lot of sense, not so surprising that result, okay? Well, this is the unbiasedness. So here you see the consistency. So what happens if n goes to infinity? So if we don't don't throw the coin 200 times, but 400 times, 600 times, 800, and so on. Very, very, very often. Then your economic intuition would say, yeah, clearly, if I now just sum up how often when I do it 1,000 times, and I count the number of heads, and I count the number of coins, I'm pretty sure that the numbers will be very close to 500 each. Well, so the percentage excess will go to zero. It will get smaller and smaller and smaller. For very small numbers of trials, you know, if I only 10 times, okay, very extreme things may happen. Well, 10 heads in a row, why not, right? But if you throw the coin 1,000 times, you know, that averages out. All right? And this is exactly here. We see here that the difference here between these various simulations gets smaller and smaller and smaller and smaller. This is exactly what consistency means. Right? I go, n goes to infinity. I have a small sample bias, probably. Yeah, I don't know. But if n goes to infinity, you know, the variations in my result here get smaller and smaller. And now, last thing we do today, very important result. Under which conditions is the ordinary least square estimator, our beta hat, blah, 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 a consistent estimator. Right? So, here are the assumptions that we do. So, again, we have the standard case, so no order correlation, no heterophysicity. But now, we only assume weakly exogenous unity. Okay, so that standard time series regression case where we have lag endogenous regressors and therefore obvious no strict exogeneity is included here. So it allows for predeterminate regressors. Okay, only this. This is a weaker assumption. Now we only want to know. So given here, if you remember that. This example with the R1 process, so yt is alpha, yt minus 1 plus ut. What we now want is that the expected value of yt minus 1 times ut is 0. This is the only thing we want to know. This is weak exogeneity. Yt minus 1, the regressor is only with the contemporaneous error uncorrelated. This is all we, this is weak exogeneity. This is all we want to know now. Strict exogeneity was although with t minus 1 and so on and so on, that was obviously not true. Okay, so then the least square estimator, here it is, and here we just plug in again what the formula of beta hat of the model, and then it looks like this. We know that formula already from the proof of unbiases. But the claim is now, in that case, the probability limit of beta hat is beta. So we have a consistent estimator if the regressors are weakly exogenous. Alright, and this is what we mean here with weaker exogeneity condition. That's important to know. Okay. Unbiasedness only under strict exogeneity. Right? Consistency, weak exogeneity is already enough. Okay? And therefore, while regressions of time series data are biased, they can still be consistent. So the bias is a small sample bias in the sense that it vanishes over time. Right? So look here again, you know, if we say consistency, yeah, here we argue that consistency means that the mean square error of the estimator goes to 0 if n goes to infinity. Right? And you see, in that case, the variance goes to infinity and the bias goes to infinity. Goes to 0. Right? So now remember, you know, our small sample bias result here. We have a bias. For each number of observations, we have a bias. Yeah? Here. we call estimator that where the bias is 0 when n goes to infinity, asymptotically unbiased. Okay? So you see, a necessary and sufficient condition for consistency is that first, the variance goes to 0 if n goes to infinity, and second, that the estimator is asymptotically unbiased, so that the bias goes to 0 if n goes to infinity. Of course, asymptotically unbiasedness is an indication of unbiasedness. Yeah? So if you have an estimator that is unbiased in small samples, meaning for each n, whatever n you take is unbiased, then of course also if n goes to infinity, it stays unbiased. Right? But there are of course examples where this does not hold, so, and this is here that slide, here. It gives you several examples for an estimator of the mean of a IID population here. Yeah, so we have here n observations taking the sample, the expected value of all these y's is mu, and now we want to estimate that parameter, and we do it very naively. Well, usually we just take, of course, the mean of it, right, and that's it. And you can show that this is the best estimator, the consistent, blah, 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 blah. But now look at these 4 alternative estimators. Okay? And now the question, and this is something we should do for next week, maybe in the tutorial, I don't know, maybe next week. So check whether these estimators here for mu are biased, asymptotically unbiased, consistent. So what happens with variance and bias and n goes to infinity? Okay, that's a nice exercise. And you can also practice then expected value of the sum, variance of the sum, blah 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 blah. Yeah. So I recommend that exercise. And next week we go a little bit to the proof of consistency of these square estimations. Okay? Thank you very much.